Brazing is a metal joining process in which two or more metal items are joined together by melting and flowing a filler metal into the joint, the filler metal having a lower melting point than the adjoining metal. Brazing differs from welding in that it does not involve melting the workpieces and from soldering in using higher temperatures for a similar process, while also requiring much more closely fitted parts than when soldering. The filler metal flows into the gap between close-fitting parts by capillary action. The filler metal is brought slightly above its melting temperature while protected by a suitable atmosphere, usually a flux. It then flows over the base metal and is then cooled to join the workpieces together. It is similar to soldering, except for the use of high temperatures. A major advantage of brazing is the ability to join the same or different metals with considerable strength. Fundamentals. High-quality brazed joints require that parts be closely fitted, and the base metals exceptionally clean and free of oxides. In most cases, joint clearances of 0.03 to 0.08 mm are recommended for the best capillary action and joint strength. However, in some brazing operations it is not uncommon to have joint clearances around 0.6 mm. Cleanliness of the brazing surfaces is also important, as any contamination can cause poor wetting. The two main methods for cleaning parts prior to brazing are chemical cleaning and abrasive or mechanical cleaning. In the case of mechanical cleaning, it is important to maintain the proper surface roughness, as wetting on a rough surface occurs much more readily than on a smooth surface of the same geometry. Another consideration is the effect of temperature and time on the quality of brazed joints. As the temperature of the braze alloy is increased, the alloying and wetting action of the filler metal increases as well. In general, the brazing temperature selected must be above the melting point of the filler metal. However, several factors influence the joint designer's temperature selection. The best temperature is usually selected to be the lowest possible braze temperature. Minimize any heat effects on the assembly. Minimize filler metal-base metal interaction. Maximize the life of any fixtures or jigs used. In some cases, a worker may select a high temperature to accommodate other factors in the design. The effective time on the brazed joint primarily affects the extent to which these effects are present. In general, however, most production processes are selected to minimize brazing time and associated costs. This is not always the case, however, since in some non-production settings, time and cost are secondary to other joint attributes. Flux. Unless brazing operations are contained within an inert or reducing atmosphere environment, a flux such as borax is required to prevent oxides from forming while the metal is heated. The flux also serves the purpose of cleaning any contamination left on the brazing surfaces. Flux can be applied in any number of forms, including flux paste, liquid, powder, or pre-made brazing pastes that combine flux with filler metal powder. Flux can also be applied using brazing rods with a coating of flux, or a flux core. In either case, the flux flows into the joint when applied to the heated joint and is displaced by the molten filler metal entering the joint. Excess flux should be removed when the cycle is completed, because flux left in the joint can lead to corrosion, impede joint inspection, and prevent further surface finishing operations. Phosphorus-containing brazing alloys can be self-fluxing when joining copper to copper. Fluxes are generally selected based on the performance on particular base metals. To be effective, the flux must be chemically compatible with both the base metal and the filler metal being used. Self-fluxing phosphorus filler alloys produce brittle phosphides if used on iron or nickel. As a general rule, longer brazing cycles should use less active fluxes than short brazing operations. Filler materials. A variety of alloys are used as filler metals for brazing, depending on the intended use or application method. In general, braze alloys are made up of 3 or more metals to form an alloy with the desired properties. The filler metal for a particular application is chosen based on its ability to wet the base metals, withstand the service conditions required, and melt at a lower temperature than the base metals or at a very specific temperature. Braze alloy is generally available as rod, ribbon, powder, paste, cream, wire and prior forms. Depending on the application, the filler material can be pre-placed at the desired location or applied during the heating cycle. For manual brazing, wire and rod forms are generally used as they are the easiest to apply while heating. In the case of furnace brazing, alloy is usually placed beforehand since the process is usually highly automated. Some of the more common types of filler metals used are aluminum, silicon, copper, copper silver, copper zinc, copper tin, gold silver, nickel alloy, silver, amorphous brazing foil using nickel, iron, copper, silicon, boron, phosphorus, etc. Atmosphere. As brazing work requires high temperatures, oxidation of the metal surface occurs in an oxygen-containing atmosphere. This may necessitate the use of an atmospheric environment other than air. The commonly used atmospheres are air, simple and economical. Many materials susceptible to oxidation and build-up of scale. Acid cleaning bath mechanical cleaning can be used to remove the oxidation after work. Flux counteracts the oxidation, but may weaken the joint. Combusted fuel gas 87% N2, 11 to 12% CO2, 5 to 1% CO, 5 to 1% H2. For silver, copper, phosphorus and copper zinc filler metals. For brazing copper and brass. Combusted fuel gas 70 to 71% N2, 5 to 6% CO2, 9 to 10% CO, 14 to 15% H2. For copper, silver, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, mono, medium carbon steels. Combusted fuel gas 73 to 75% N2, 10 to 11% CO, 15 to 16% H2. For copper, silver, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, mono, medium and high carbon steels. Combusted fuel gas 41 to 45% N2, 17 to 19% CO, 38 to 40% H2. For copper, silver, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, medium and high carbon steels. Ammonia. Dissociated ammonia can be used for many types of brazing and annealing. Inexpensive. For copper, silver, nickel, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, mono, medium and high carbon steels and chromium alloys. Nitrogen plus hydrogen, cryogenic purified, 70 to 99% N2, 1 to 30% H2. For copper, silver, nickel, copper, phosphorus and copper zinc filler metals. Nitrogen plus hydrogen plus carbon monoxide, cryogenic purified, 70 to 99% N2, 2 to 20% H2, 1 to 10% CO. For copper, silver, nickel, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, medium and high carbon steels. Nitrogen, cryogenic purified, non-oxidizing, economical, at high temperatures can react with some metals, e.g., certain steels, forming nitrides. For copper, silver, nickel, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, mono, medium and high carbon steels. Hydrogen, strong deoxidizer, highly thermally conductive, can be used for copper brazing and annealing steel. may cause hydrogen embrittlement to some alloys. For copper, silver, nickel, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, mono, medium and high carbon steels and chromium alloys, cobalt alloys, tungsten alloys, and carbides. Inorganic vapors, special purpose, can be mixed with atmospheres AWS 1 to 5 to replace flux. Used for silver brazing of brasses. Noble gas, non-oxidizing, more expensive than nitrogen. Inert parts must be very clean, gas must be pure. For copper, silver, nickel, copper, phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, mono, medium and high carbon steels, chromium alloys, titanium, zirconium, hafnium. Noble gas plus hydrogen. The vacuum requires evacuating the work chamber. Expensive. Unsuitable for metals with high vapor pressure, e.g., silver, zinc, phosphorus, cadmium and manganese. Used for highest quality joints, for e.g., aerospace applications. Common techniques. Torch brazing. Torch brazing is by far the most common method of mechanized brazing in use. It is best used in small production volumes or in specialized operations, and in some countries, it accounts for a majority of the brazing taking place. There are three main categories of torch brazing in use: manual, machine, and automatic torch brazing. Manual torch brazing is a procedure where the heat is applied using a gas flame placed on or near the joint being brazed. The torch can either be handheld or held in a fixed position depending on whether the operation is completely manual or has some level of automation. Manual brazing is most commonly used on small production volumes or in applications where the part size or configuration makes other brazing methods impossible. The main drawback is the high labor cost associated with the method, as well as the operator skill required to obtain quality brazed joints. The use of flux, a self-fluxing material, is required to prevent oxidation. Torch brazing of copper can be done without the use of flux if it is brazed with a torch using oxygen and hydrogen gas, rather than oxygen and other flammable gases. Machine torch brazing is commonly used where a repetitive braze operation is being carried out. This method is a mix of both automated and manual operations, with an operator often placing brazes material, flux and jigging parts while the machine mechanism carries out the actual braze. The advantage of this method is that it reduces the high labor and skill requirement of manual brazing. The use of flux is also required for this method as there is no protective atmosphere, and it is best suited to small to medium production volumes. Automatic torch brazing is a method that almost eliminates the need for manual labor in the brazing operation, except for loading and unloading of the machine. The main advantages of this method are a high production rate, uniform braze quality, and reduced operating cost. The equipment used is essentially the same as that used for machine torch brazing, with the main difference being that the machinery replaces the operator in the part preparation. Furnace brazing. Furnace brazing is a semi-automatic process used widely in industrial brazing operations due to its adaptability to mass production and use of unskilled labor. There are many advantages of furnace brazing over other heating methods that make it ideal for mass production. One main advantage is the ease with which it can produce large numbers of small parts that are easily jigged or self-locating. The process also offers the benefits of a controlled heat cycle and no need for post-braze cleaning. Common atmospheres used include inert, reducing, or vacuum atmospheres, all of which protect the part from oxidation. Some other advantages include low unit cost when used in mass production, close temperature control, and the ability to braze multiple joints at once. Furnaces are typically heated using either electric, gas, or oil depending on the type of furnace and application. However, some of the disadvantages of this method include high capital equipment costs, more difficult design considerations, and high power consumption. There are four main types of furnaces used in brazing operations: batch type, continuous, retort with controlled atmosphere, and vacuum. A batch type furnace has relatively low initial equipment costs and can heat each part load separately. It can turn on and off at will, which reduces operating expenses when it's not in use. These furnaces are suited to medium to large volume production, and offer a large degree of flexibility in type of parts that can be brazed. Either controlled atmospheres or flux can be used to control oxidation and cleanliness of parts. Continuous type furnaces are best suited to a steady flow of similar-sized parts through the furnace. These furnaces are often conveyor-fed, moving parts through the hot zone at controlled speed. It is common to use either controlled atmosphere or pre-applied flux in continuous furnaces. In particular, these furnaces offer the benefit of very low manual labor requirements and so are best suited to large-scale production operations. Retort-type furnaces differ from other batch-type furnaces in that they make use of a sealed lining called a retort. The retort is generally sealed with either a gasket or is welded shut and filled completely with the desired atmosphere and then heated externally by conventional heating elements. Due to the high temperatures involved, the retort is usually made of heat-resistant alloys that resist oxidation. Retort furnaces are often either used in a batch or semi-continuous versions. Vacuum furnaces is a relatively economical method of oxide prevention and is most often used to braze materials with very stable oxides that cannot be brazed in atmosphere furnaces. Vacuum brazing is also used heavily with refractory materials and other exotic alloy combinations unsuited to atmosphere furnaces. Due to the absence of flux or a reducing atmosphere, the part cleanliness is critical when brazing in a vacuum. The three main types of vacuum furnace are single-wall hot retort, double-walled hot retort, and cold-wall retort. Typical vacuum levels for brazing range from pressures of 1.3 to 0.13 pascals to 0.00013 pascals or lower. Vacuum furnaces are most commonly batch type, and they are suited to medium and high production volumes. Silver brazing. Silver brazing, sometimes known as a silver soldering or hard soldering, is brazing using a silver alloy-based filler. These silver alloys consist of many different percentages of silver and other metals, such as copper, zinc and cadmium. Brazing is widely used in the tool industry to fasten hard metal tips to tools such as saw blades. Pre-tinning is often done. The braze alloy is melted onto the hard metal tip, which is placed next to the steel and remelted. Pre-tinning gets around the problem that hard metals are hard to wet. Brazed hard metal joints are typically 2 to 7 mils thick. The braze alloy joins the materials and compensates for the difference in their expansion rates. It also provides a cushion between the hard carbide tip and the hard steel, which softens impact and prevents tip loss and damage. Much as a vehicle's suspension helps prevent damage to the tires and the vehicle. Finally, the braze alloy joins the other two materials to create a composite structure, much as layers of wooden glue create plywood. The standard for braze joint strength in many industries is a joint that is stronger than either base material, so that when under stress, one or other of the base materials fails before the joint. One special silver brazing method is called pin brazing or pin brazing. It has been developed especially for connecting cables to railway track or for cathodic protection installations. The method uses a silver and flux-containing brazing pin, which is melted in the eye of a cable lug. The equipment is normally powered from batteries. Braze welding. Braze welding is the use of a bronze or brass filler rod coated with flux to joint steel workpieces. The equipment needed for braze welding is basically identical to the equipment used in brazing. Since braze welding usually requires more heat than brazing, acetylene or methylacetylene propylene gas fuel is commonly used. The name comes from the fact that no capillary action is used. Braze welding has many advantages over fusion welding. It allows the joining of dissimilar metals, minimization of heat distortion, and can reduce the need for extensive preheating. Additionally, since the metals joined are not melted in the process, the components retain their original shape. Edges and contours are not eroded or changed by the formation of a fillet. Another effect of braze welding is the elimination of stored-up stresses that are often present in fusion welding. This is extremely important in the repair of large castings. The disadvantages of the loss of strength when subjected to high temperatures and the inability to withstand high stresses. Carbide, cermet and ceramic tips are platted and then joined to steel to make tipped band saws. The plating acts as a braze alloy. Cast iron welding. The welding of cast iron is usually a brazing operation, with a filler rod made chiefly of nickel being used, although true welding with cast iron rods is also available. Ductile cast iron pipe may be also CAD welded, a process that connects joints by means of a small copper wire fused into the iron when previously ground down to the bare metal, parallel to the iron joints being formed as per hub pipe with neoprene gasket seals. The purpose behind this operation is to use electricity along the copper for keeping underground pipes warm in cold climates. Vacuum brazing. Vacuum brazing is a material joining technique that offers significant advantages. Extremely clean, superior, flux-free brazed joints of high integrity and strength. The process can be expensive because it must be performed inside a vacuum chamber vessel. Temperature uniformity is maintained on the workpiece when heating in a vacuum, greatly reducing residual stresses due to slow heating and cooling cycles. This, in turn, can significantly improve the thermal and mechanical properties of the material, thus providing unique heat treatment capabilities. One such capability is heat treating or edge hardening the workpiece while performing a metal joining process, all in a single furnace thermal cycle. Vacuum brazing is often conducted in a furnace. This means that several joints can be made at once because the whole workpiece reaches the brazing temperature. The heat is transferred using radiation, as many other methods cannot be used in a vacuum. Dip brazing. Dip brazing is especially suited for brazing aluminium because air is excluded, thus preventing the formation of oxides. The parts to be joined are fixtured and the brazing compound applied to the mating surfaces, typically in slurry form. Then the assemblies are dipped into a bath of molten salt, which functions as both heat transfer medium and flux. Heating methods. There are many heating methods available to accomplish brazing operations. The most important factor in choosing a heating method is achieving efficient transfer of heat throughout the joint and doing so within the heat capacity of the individual base metals used. The geometry of the braze joint is also a crucial factor to consider, as is the rate and volume of production required. The easiest way to categorize brazing methods is to group them by heating method. Here are some of the most common: torch brazing, furnace brazing, induction brazing, dip brazing, resistance brazing, infrared brazing, blanket brazing, electron beam and laser brazing. Braze welding. Advantages and disadvantages. brazing has many advantages over other metal joining techniques, such as welding. Since brazing does not melt the base metal of the joint, it allows much tight control over tolerances and produces a clean joint without the need for secondary finishing. Additionally, dissimilar metals and non-metals can be brazed. In general, brazing also produces less thermal distortion than welding due to the uniform heating of a brazed piece. Complex and multi-part assemblies can be brazed cost-effectively. Welded joints must sometimes be ground flush, a costly secondary operation that brazing does not require because it produces a clean joint. Another advantage is that the brazing can be coated or clad for protective purposes. Finally, brazing is easily adapted to mass production, and it is easy to automate because the individual process parameters are less sensitive to variation. One of the main disadvantages is the lack of joint strength as compared to a welded joint due to the softer filler metals used. The strength of the brazed joint is likely to be less than that of the base metal but greater than the filler metal. Another disadvantage is that brazed joints can be damaged under high service temperatures. Brazed joints require a high degree of base metal cleanliness when done in an industrial setting. Some brazing applications require the use of adequate fluxing agents to control cleanliness. The joint color is often different from that of the base metal, creating an aesthetic disadvantage.